All right, so we're continuing to talk about slopes of tangent lines. And so hopefully you understand, but how do we know we're doing this perfectly? If I just draw a curve like so, and I have this point, right? Someone might come along and say like, all right, here I am drawing the tangent line, right? That green thing certainly looks like it's doing a pretty good job. But maybe someone else will draw it slightly differently, right? This pink thing, when I zoom in, it's also doing a pretty good job. How do we know which one is perfect? Because I didn't really give you a specific definition. I just said it's the line that captures the direction. And it feels like maybe there are more ways to do this than just one. There's some guesswork. How do I know which one is best? We would like to be able to do this in a systematic way. So let me walk you through this. We have to explain it a little bit abstractly so we can apply the same idea to any particular tangent line we're thinking about. So let's imagine we just have some curve like so. And I am trying to figure out how steep is the tangent line at that particular point. Right? So I'm kind of imagining, in my head, what does it look like? So something like so seems to be the steepness. But instead of talking about the tangent line, let's talk about what's called a secant line. So a secant line is a line connecting two different points on a graph. So let's just imagine down here is our x-axis, maybe over here is our y-axis. And let's just call this x-coordinate x, just a generic x. Let's imagine that we go forward by a certain distance, and I'll call it delta x. Delta often represents a change. So we're imagining, what if I start with x? Oops. What if I start with x and change it a little bit? I will move it forward. So this new x-coordinate would be x plus delta x. I took x and I changed it a little bit, so I had added that new amount. And there would be this new point on the graph there. Let's assume that this is the function y equals f of x. So we're being kind of generic here. This point has an x-coordinate we just call x, so its y-coordinate would be f of x. I haven't said which function this is, I'm just calling it f. Over here, this has an x-coordinate that we will call x plus delta x, and so it has a corresponding y value of f of x plus delta x. And let's just notice, x plus delta x is our entire input. All of that is inside the parentheses. This is not f of x, so let me just put this on the side. Right. F of x plus delta x is not the same as f of x, and then I add delta x. Here, all of this is the input. The input has the addition inside. We are not just figuring out f of x and then adding when we're done. So now I could draw what's called a secant line. Right, so we'll notice this secant line is not quite the same as the blue line, but we could find the slope of that secant line. So we'll write m sec. Right, the slope of the secant line would be the change in y over the change in x. And if we go down here, we'll notice, right, change in y over change of x. This is a y-coordinate, and this is a y-coordinate. So this is what I get when I subtract the y's. Change in x would be this x-coordinate minus this x-coordinate, which is down here. Okay, so the top is the change in y, the bottom is the change in x. And we'll notice in the bottom, the x's would cancel, and we really are just left with delta x. So this is a very abstract formula, but you want to understand where it comes from. This top is just the change in the y value, right? Our new y value, our new value of f, minus our previous one. And then this is the change in x, which we just call delta x. You want to know and understand this. You will need to have this at your fingertips. Don't just memorize it in a vacuum. You want to understand know, and memorize. I'll put memorize in quotes because it should not just be pure memorization. Your memory of this should reflect your understanding of where it comes from. And the good news is once we start putting specific formulas or numbers in there, you can probably simplify something. Right? So just file that away. When you use this, often nice things will happen from an algebraic point of view. Okay, so what we have here, again, is the slope of a secant line. This line in green connects two different points. We're theoretically trying to figure out this tangent line that I'll temporarily draw in pink. Maybe that's the tangent line. And what we'll notice is the steepness of this specific tangent line and the steepness of this secant line, they're pretty close. And it turns out they'll be even closer if these points were closer together. Right, so theoretically, imagine that I put my orange point over here. Right, so I'm going to hide the pink. I know this diagram's getting a little busy. I'm going to hide the pink and imagine that my second point was right here. If I drew the secant line between these 2 points that were super close together, that secant line would look even more like a tangent line. Right? When the points are really close together, when I zoom in close to the red point, that secant line in pink seems to be doing exactly what the original graph in blue does because it's behaving like a tangent line. So this is the observation. I say something similar to this in this paragraph, but our observation is that when 2 points are very close together, the secant line resembles a tangent line. Let me show you in Desmos. So let's hide this, let's hide this, let's hide this. Okay, don't worry about where all this stuff is coming from. Okay, so here I have this graph in red, and I want to draw its tangent line at the origin. So I actually have a slider here. So here's what I can do. I can create a secant line. So right now I'm drawing the secant line between that highlighted point on the lower left and the origin at 0, 0. And that secant line just seems to be random. It doesn't have much in common with the red curve. But if I move this secant point closer to 0, let me zoom in if I can. Sorry, let me fix this. So here in the upper left is the highlighted point that we're thinking of as the second. Oh, okay. Let me see if I can fix this. Sorry. Okay, yeah, let's do this. A goes from -1 to 0 with steps of 0.01. So I'm really going to control this well. As I move that purple highlighted point, I'm drawing the secant line. As that second point moves closer and closer to the origin, what you're noticing is that the blue secant line becomes more and more similar to the red graph. It becomes closer to a tangent line. Right, so right now, it's still technically a secant line. It's connecting 2 different points. But if those points are really close together, if I zoom in here, it's really hard to tell the difference between the secant line and what a tangent line would be doing. When the 2 points are really close together, secant lines behave like tangent lines. And in theory, we would want them to be so close together that that distance between them is zero. Right? This is what we're moving towards, right? We want them to be in the same place. We want the distance to be zero. Now the problem is, if delta x is zero, we're dividing by zero, which we're not allowed to do. So we're gonna do the next best thing. We're not gonna literally plug in zero, but we're gonna do the limits as that distance approaches zero. So here is our formula for finding the slope of a tangent line. Assuming we have some graph and some specific x coordinate, the slope of the tangent line is the limit as that distance, as delta x gets tinier and tinier, as delta x approaches zero, of the slope of the secant line, which we saw before is this formula. So you'll need to know this. It's the same formula as before with the limit in front of it. And again, the more you understand this, the less it will feel like memorization. Let me show you an example. Right, so even if you're taking notes, watching this on Edpuzzle, just watch this happen. Don't feel like you have to copy this because you're going to do a similar example in a second. So what if I want to find the slope of the line tangent to the graph of y equals the square root of x at the point 9, 3? I'll go back to Desmos just to get a good look at this. So here is my graph, and I've put a little dot at 9, 3. Right? So I want to measure what is the steepness there. As I zoom in, it kind of looks like a line. How steep is that line? Well, let's use this formula. So the most general formula here is that the slope of the tangent line will be the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. And for this particular problem, the function we're thinking about is the square root function. And the x coordinate where we're doing this calculation is 9. So now I'll move from this general formula to specifically for this problem. It'll be the limit as delta x approaches 0. Right? And delta x doesn't mean delta times x. It's just the name of the width. F is the square root function. So it's some value of f minus some other value of f. X is 9. So it is the square root of 9 plus delta x, because 9 plus delta x is the same as x plus delta x. And f is the square root function, minus the square root of 9, because x is 9. And the bottom is delta x. Hopefully I've given myself enough room. You are not copying this, so if I need to erase something, it's not a problem. Square root of 9 is 3. So I want to do this limit. We always want to try plugging in. What if delta x is 0? Then this is the square root of 9, which is 3, and we have 3. So the top is 3 minus 3, which is 0, but the bottom is also 0. So this is one of these dreaded 0 over 0 limits with a radical. So hopefully remember that our trick is we look at this part with the radical and subtraction, and we will multiply by its conjugate. Of course, we have to multiply the bottom by the same thing. Hopefully you remember the trick where when we multiply together a conjugate pair, it is just the first thing squared minus the second thing squared. So that would be 9 plus delta x minus 3 squared, which is 9. In the bottom, I am going to leave it factored until I have reason to believe it would be better to do something else. Okay. I notice that 9 minus 9 cancels. Hopefully I can squeeze in my answer here. Again, no one asked you to copy this, so don't worry about where you put it. My numerator is just delta x my denominator is delta x times this stuff that's been in parentheses. Delta x in top cancels with delta x in the bottom, leaving just a 1 in the numerator. And now let's try plugging in again. What if delta x is 0? Then I have 1 over the square root of 9 plus 0 plus 3. That's 1 over 3 plus 3, which is 1/6. So this, this is a little tricky. One of the reasons why we began the class with all of these limit rules and all of these tricks for evaluating limits is because this is when we really want to use them. It is so important to be able to figure out steepnesses. So the limit will be helpful there. And we got 1/6. So if I go back to this graph, I will actually type in point slope. What if that line has a slope of 1/6? So y minus my specific x coordinate equals slope, which I think is 1/6, times x minus my specific x coordinate. And it really looks like I have that perfect. At that point, 1/6 is measuring the slope. Excuse me. Now, one thing that I really want to warn you about is this thing with f of x plus delta x. It is not the same. I'm going to write this again. F of x plus delta x is not the same as f of x, and then I add delta x. We need to look at this as a unit. This is the input. And we apply the function to the entire input. In this previous example, the function was the function that takes the square root. So we were taking the square root of this entire input, 9 plus delta x. All of this is under the radical because I'm taking the square root of the whole thing. I'm not just taking the square root of 9 and adding. I'm taking the square root of 9 plus delta x all together inside this radical. Really pay attention to that because it's the most common mistake that people make in these cases. All right, so now let's try another one. Right, and it's still a little tricky. I'll go through step by step, but I'll sort of nudge you to anticipate my steps. So let's go back to that original problem. We already saw the picture. I just kind of told you what the tangent line is, but let's see if we can figure out where that comes from. So we have y equals x squared plus x at the point 2, 6. Right, there's a typo here. Make sure you have 2, 6 rather than what I put before. So the function we care about is x squared plus x, and the specific location we care about is at x equals 2. So our most generic way of writing this, let's just practice writing that first step, is f of x plus delta x minus f of x all over delta x. And let's just replace those x's with 2. We want to know what's happening specifically at the place where x is equal to 2. All right, so we need to make sense, we need to make sense of this expression, which means you really need to make sense of what is the function f doing. And we saw some of this in the preliminary sections. Look at this function and describe what f is doing using the word input instead of the name x. Right? Think about that. How would you describe what does f do to its input? Don't use the name x. What this is really doing is it's saying input squared plus the input. Whatever my input is, I square it, and then I add the input. Maybe my input is 2, maybe my input is called x, maybe my input is called 7, maybe my input is called 2 plus delta x. We want to understand what the function is doing in a really general way. So let's use this. And here's something that I am going to strongly recommend. Anytime you have a function with any degree of complexity, probably a good idea is to separate these and put them in brackets, because otherwise you might forget to distribute that negative. So let's think about what we've got here. I have my brackets. F of 2 plus delta x means input squared plus input. So write out, what would that look like for this? Hopefully you have quantity 2 plus delta x squared plus quantity 2 plus delta x. And then minus, right, what number do you get if you plug in 2? You get 2 squared plus 2, which is 6. Right, so I'm just going to go ahead and write 6. Maybe you did that in your head. And our bottom is delta x. Do not forget about the delta x at the bottom. And do not forget about the limit. Keep writing the limit of every stage. You need to remember this is a limit problem. And here's the thing I'm going to tell you. This thing looks like a mess, but it is highly likely to simplify after we do the algebra. If it's not simplifying, maybe you've done your algebra incorrectly and go look. I know this looks like a mess. I promise it's actually going to be pretty nice after we simplify everything. So I will try to squeeze this in. My space management is not fantastic. Okay, what do we got here? If I FOIL this out, right, remember, let's put this on the side. Another mistake people make a lot, right? 2 plus delta x squared, the quantity squared, is not the same as 2 squared plus delta x squared. That's not how it works. 2 plus delta x squared means 2 plus delta x times 2 plus delta x. Do the foiling. Don't just square first and last. Another super common mistake. You'll get the wrong answer. So if we FOIL out this thing, our firsts would be 2 times 2, which is 4. Our outers and inners would be 2 times delta x, and we'd get that twice. And then we'd have the last would be delta x squared. I'm just going to write it like this. Remember, this is not multiplication. Delta x is the name of something. And then we have plus 2 plus delta x minus 6. And there's still this delta x in the bottom. All right, I'm going to have to cheat a little bit and add a new page. I did not plan this well. I apologize if you're taking notes and it's all messed up. Let's continue to simplify this. Oops, I didn't want to do that. I wanted to copy it, not cut it. Okay, so let's look at what we have here. Remember, we are expecting cancellation. And I'll tell you right now, if you plug in, obviously we're dividing by 0. So we have to simplify first. I will notice that my constants, I have 4 plus 2 minus 6. So the constants are actually 0. In terms of delta x, I have 4 copies of delta x plus 1 copy of delta x. So if I group those together, I have 5 copies of delta x. And then I also have 1 copy of delta x squared. And delta x in the bottom. It's still a 0 over 0 limit, so let's do our favorite trick, which is factor and cancel. In this numerator, you can just factor out the delta x. And for a wide variety of problems, that's what's going to happen. You're going to expect that probably everything without a delta x cancels, and I can factor it out. So now we see there's a delta x factored out of the top. There's a delta x in the bottom. We can eliminate those by dividing top and bottom by the same thing. Now we can plug in, and our answer is 5, which is what we saw before. Going back to the graph. At that point, at that point, 2, 6 on the graph of x squared plus x, the tangent line had a slope of 5. Specifically, it was 5, y equals 5x minus 4. This is not quick, but you should be able to get there. You need to understand the pattern and then just step by step answer questions like, well, what number is x to do this problem? Where am I looking? Which function am I taking? Right? And make sure you understand it in terms of input and not just the letter x. And if you do all of this carefully and know your algebra and know your limit rules, you will get there. You're not going to have to do this forever. At some point, we will notice patterns so that we don't have to do this. But in the short term, know how to do this. Okay, we'll stop